Hello and greeting everyone. My name is Ansar Karim Mustafa. Our topic today is torsion path, lecture named Dr. Izzuddin. First of all, I would like to introduce my group members, which are Anas Abdul Karim, Muhammad Amir, and Muhammad Amir Lazurgi, and Mubarak bin Muhammad, and Muhammad Ashraf Fahmi. The first part in our presentation is objective. Our objective is to investigate the relationship between the torque and the angle twist of a circular or rectangular cross-section bars and determine the models of rigidity G of the material. Then the second part of our presentation is the introduction. The torsion is studied by evaluating the stress and the strain in the circular cross-section members subjected to twisting couples or torques. And these couples have common magnitude and opposite signs, and they are vector magnitude, and they can be either represented by curved arrows or the couple of vectors. The general formula TL divided on JG, where the T is the torque and L is the length and G is the modulus of rigidity, and G is equal to the pi D divided on 32 on polar models, and D is the diameter and the angle twist. Then the torsion members are used in the variety of engineering application. A transmission shaft provided the most common use, which are used to transmit the power from one point to another. For example, a shaft is used to transmit the power from the engine to the rear wheels of the automation, and this shaft can be either solid or hollows.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ashraf Fahmi bin Muhammad Nazri. So I'll explaining for my part, which is theory for this experiment, which is experiment 6. Shearing can be measured by the angles formed by the sides of the element, where we can see in the equation in the slide, which is length times shear strain is equal to length from the center to any point in the circle of the shaft times angle of twist, which is L times lambda is equal to P times theta. So we can simplify the equation, become lambda is equal to P theta divided by L. Other than that, the shear strain is a maximum on the surface of the shaft, where the length from the center to any point in the circle of the shaft is equal to the radius of the shaft, which is P is equal to C. So we can get the lambda maximum, which is shearing strain maximum, is equal to C, which is radius of the shaft, times angle of twist divided by L. We also need to consider the Hooke's law, where the Hooke's law is being applied when the yield stress is not exceeded anywhere in the shaft in the elastic range. So we can get the where we can get the equation for shear stress maximum is equal to shearing stress maximum times G, where G is symbolized for modulus of rigidity. Other than that, the shear stress equation is T times C divided by J. So when we substitute the equation in order to get the equation of angle of twist, so we can get the angle of twist. The equation for angle of twist is equal to T top times L length divided by J, where J is polar moment of inertia, times G modulus of rigidity. So here I want to clarify the J for has a different equation to find. For example, for solid bar has different J, and for hollow bar has different J. So here is the what I said before. The moment of inertia areas has a different for different type, different size or different shape. So that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amir Fidaus bin Ismail, and now we will move on to the methodology. So this is the machine that we will use to make the torsion of bar experiment. For the first step, the copper hollow rod was clamped into position and load hanger was placed into the cord. Before taking any readings, the rotation scale was set up to 10 centimeters from the fixed clamp and the pointer was set to 0. The third process is the twist of every specimen was recorded in 5 Newton increment until we reach 25 Newton. Next, the load was removed. The distance between fixed clamp and the scale now is changed to 20 centimeter. The angle of twist was recorded from that distance. After taking all the measurement and the angle of twist, the procedure was repeated using a fine rod. And for the final step, the torsion head effective diameter and diameter of rod was measured and recorded using the electronic vernier calipers.
Hello, Assalamu alaikum. My name is Mohammed Lazirgi and I'm going to present the results for the experiment of torsion of bars. So first we have this table which presents information about the rods. So first we have the solid rod and note that both of the solid and the hollow rods are from copper alloy. So that's what we can say. First here they have the same modulus of rigidity, which is 45 gigapascal, and for the solid they have an outer diameter of 6 millimeters and the moment of inertia, which is pi over 2 times r to the power of 4, and we have here the result 2.03575 times 10 to the power of minus 9. For the hollow rod, we have the outer diameter 6 and the inner diameter is 3.5. So using the equation pi over 2 times C2 times of 4 minus C1 to the times of 4, and of course we've got here 1.8 times 10 to the power of minus 9. Also the radius of the shaft is 111.45 millimeters. So first here we have the solid bar. So note that the equation for the moment or torque is 4 times the radius. So we do here experiment by the loads from 5 to 30 using a 5 Newton increment, and we can see here the angle of twist by degree varies from 1 up to 7 when the pointer from the fixed clamp is 10 centimeters. And we got here the torque varies from 0.55 up to 3.34. Now it's the same solid bar, but we change the pointer from the fixed clamp to 20 centimeters, and we can see here we have a bigger angle of twist which varies from 1 up to 10 degrees, and we have here the torque is the same. And for the hollow bar, for the copper alloy, the pointer from the fixed clamp is 10 centimeter, so we got here the angle of twist is from 1 to 7 degrees, and the torque is from 0.574 to 3.4. And same here we can see the when we change to 20 centimeters, the angle of twist almost doubles. You can see here 2, 4, 6, 8, 10 and 12. If we return back, we can see how they're almost the double of the angle of twist. So here's a simple graph which represents the load, the torque based the load, which have a linear relationship, and this is the relationship between the angle of twist and the torque, which you can see as an almost linear. Okay, here we are comparing for the solid rod the angle of twist when having 10 centimeter from the fixed clamp and 20 centimeter. We can see they start almost the same, then it got higher, as I said, it's almost the double. Now this is the same for the hollow rod. We can see we have similar graph for the solid rod because the difference between the two still uh, the same, which is almost double. And that was all for me, I think.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Today, my name is Mubarak Makri, and today I'm going to talk about discussion for experiment 6. For the first discussion, to what extent does the experiment verify the torque or twist formula based on the graph plotted? So, based on the graph, the angle twist is directly proportional to torque and is proven by angle twist formula. The greater specified torque, the greater angle of twist of the circular cross-section specimen. Next, second discussion, comparison between three types of bar with different length of rotation scale and pointer from the fixed clamp. The discussion asks us to do three type of bar, but because in this experiment we only do two type of bar, so I will only explain two type of bar in the discussion. So for the first type of bar, which is hollow rod, for 100 millimeter length of rod, it showed the increase of load applied resulted in the increase of torque and the angle of twist. The graph shows a linear trend, but the increase is lower when compared to 200 milliliter length. For solid rod, for both 100 and 200 milliliter length, there is some slightly different between graph from hollow rod, but the graph still show a linear trend. In conclusion, the trend for the two specimens are the same, where the torque and angle of the twist is directly proportional in their relationship. And last, third discussion, based on your finding, explain the relationship between the modulus of rigidity of material with the parameters such as type of material for the bar, length of the bar, the shape of the bar, and polar moment of inertia. So for the discussion, based on our experiment, the relationship for modulus of rigidity with the length of the bar is the longer length of the bar, the bigger the modulus of rigidity. In other words, the length is directly proportional with modulus of rigidity. However, same material will have the same modulus of rigidity as calculated in solid and hollow bar. Besides of that, we can also determine that the shape of bar does not affect the modulus of rigidity, since shape of the bar only affect the polar moment of inertia.